Alright, so today we want to go into series and parallel circuit. Series and parallel circuit. Alright, so previously in, I think is in Form 3, if I'm not mistaken. Either Form 2 or Form 3. You also got learn a little bit about series and parallel circuit. Okay, so in last time in lower form science, you learned that how to calculate the total resistance, how to calculate the total voltage, how to calculate the total current in series and parallel circuit. Okay, so now here in physics, what we are going to learn is the reason. Why is it that the way that we calculate the current is this way, why the voltage is this way, why the resistance is in such a way. So this is very important for you to understand how is it that the charge flow in series and in parallel circuit. This is very important because this idea of understanding how the charge flow in the circuit will determine whether you understand the later chapter about electronics. If I'm not mistaken, is in chapter 5. Okay, you learn about electronics, arrangement of the circuit and so on. So this basic knowledge is very important, how the charge flow in the circuit. Okay, so let's take a look at series circuit. Okay, so in series circuit, why is it that in series the current is all the same? Okay, you say because there's only one path. So why is it that when there's only one path, then the current will be the same? Okay, the reason is because the charge flow, because of potential energy, different in charge between two points. Okay, so for example, this power source, let's say it have, let's say here the example, okay, let's say 6 volt. Okay, let's say this power source have 6 volt. Okay, 6 volt. So 6 volt means that it is able to do the work of 6 joule to drive 1 coulomb of charge from here to here. From here, go around the circuit and then to here. 6 joule of energy for every 1 coulomb of charge. So why is it that when there is 6 joule of energy, then the charge can flow? Actually, the main reason why the charge can flow is because the difference in charge. This is positive, this is negative, right? So that means the positive part have strong positive charge, the negative part have strong negative charge. So the negative will repel the electron and the positive will attract the electron. So that's why the electron can flow from the negative to the positive. So the greater the... Okay, so because of the difference in charge, one side repel, one side attract, then the charge can flow. So electron, remember the one that flow is electron. Proton cannot flow one. The one that flow is electron. So the electron flow from the negative terminal to the positive. But we take it that the current flow from positive to negative because the current that we are talking about is the conventional current. Actually, in lower form also you got learn about the difference between electron flow and conventional current. So I don't want to talk too much about that. But I just want to point out that electron flow from negative to positive, current flow or the conventional current is from positive to negative. Okay? Alright, so the current, every time we talk about current, we talk about what we mean is the conventional current, which is flow from positive to negative. We are not talking about the flow of electron. Okay? If we talk about flow of electron, the electron flow from negative to positive. Okay? Alright, back to what we discussed previously, which is why is it that if there's only one path, then the current will all be the same because of the difference in the charge. So in any point in the whole circuit, in any 2 points, for example this point and this point, between this point and this point, okay, this side is positive, so attract, this side is more negative, repel. Understand? The charge is different. You can imagine like, okay, inside the wire is filled with electron, right? Because inside the wire is all atom inside the wire, right? So every single atom have electron. Okay, so that means the electron inside the wire is full of electron. Here got electron. Okay, all full with electron. Okay, all full with electron. So when here repel, this electron will go forward because being repelled, right? It move forward, and then what will happen? The distance between the two electrons become very near, right? When near, what happen? Negative, they will repel. But repel in which direction? Of course, continue in this direction, because it will not be able to go back. Because this side is the power source, so the negative is very strong. This side, understand? So that means at the back, it will push, and then this one will push this one, push, repel. And then in front here, this electron will be attracted. So that means here, less negative, right? The negative charge will be less. And then at the back, that means you compare this point. You compare this point with this point. When the electron here go here already, so this point, the negative charge become weaker compared to this point, right? So that means this part is stronger negative charge. It will repel. And then the electron will be able to go forward. Understand? When this one go forward, this one become, the negative charge become weaker. So at the back, repel. So one side attract, one side repel, then the charge can flow. You get the idea? Okay? Anybody do understand? Anybody cannot imagine? You just imagine like, for example, you want to go back, and then the road, the lorong, okay, to go to the gate is only one person can pass through. The lorong is very tight, okay. The corridor is very narrow. Thank you very much. Okay, I forgot the word. Okay, very narrow. So only one student can pass through at one time. So the only way that you can go forward is you must wait people in front to go forward, right? And then when people in front go forward, people at the back will push you, People say, hey, in front go already, why you are still standing there? And then people at the back will push you, Even you don't want to go forward, people at the back will also push you. Okay? Get the idea? So, like that. So everybody will move at the same rate. Move at the same speed, right? Everybody move at the same speed. Okay? People in front go fast, you will go fast, people at the back will go fast. People in front go slow, you will go slow, people at the back will go slow. So everybody will only be able to move at the same rate. So this is the idea. Why is it that in series circuit, the charge all flow at the same rate? Okay, get the idea? Okay, so let me back because the diagram become very untidy. Okay, alright. Now, so how about this one? Here got voltmeter, right? So is the current, is the charge going to go here or not? No, why not? Why not? Because the voltmeter have extremely high resistance. Okay, we just take it that the resistance is so high that no charge will be able to flow through, Okay, it's so high that the amount of charge that pass through can be ignored. Understand? Okay, so that means even here got voltmeter connected in parallel. This is still series circuit, still one path only. Understand or not? Still one path only. So, anybody have any question? No question. Okay, all right. If you got question, please ask. Okay, now, so here this current, and this current 1, current 2, current 3, and this current is all the same lah. So this current is the total current lah. Why we say that this is the total current or the biggest current? Because this is the current that is directly from the power source. You see, this current is direct from the power source. So this is, we say, as the total current or the main current. So this main current and all of these other current is the same. Okay, all the same. Alright, next, we want to look at the potential difference at every point. Okay, potential difference at every point. So, if you still remember previously, we discussed that if you still remember previously, we discussed that, let's say that the charge that come out here, every 1 coulomb carries 6 joule. So the 1 coulomb of charge when reach here, the first resistor, let's say that it do the work of 1 joule, 1 coulomb. 1 coulomb do the work of 1 joule. And then when pass through the second one, let's say 1 coulomb do the work of 3 joule. And then when pass through this one, the third one, every 1 coulomb do the work of 2 joule, for example. Do the work of 2 joule. So that means the potential difference here will be 1 volt. This one will be 3 volt. This one will be 2 volt. Very good. So total will be 6 volt lah. So you see here, work done here is 1 joule, here is 3, here is 2. So from here to here, total is 6 joule for every 1 coulomb. So that means this voltmeter that measure the total voltage. Why is it that this voltmeter measure total voltage? Because it measure from the beginning of the power source to the end of the power source. You see or not? Okay, in between here and here, there's no other thing that use energy. Okay, so this is the total voltage. So the total voltage, 6 volt, is equal to the voltage 1 plus voltage 2 plus voltage 3 lah. Or the potential difference lah. Okay, when I say voltage, I mean potential difference lah. So the total potential difference will be potential difference 1 plus potential difference 2 plus potential difference 3. Right, this is something that you learn in lower form. Now you learn the reason why is the total potential difference or the total voltage is like that. We add all together. Okay, now we want to learn how to calculate the total resistance. Okay, so here we have R1, R2, R3. So how do we calculate the total resistance? So let's say that okay, so we want to derive the equation that we use to calculate the total resistance. So let's say that, so we use this one, V equals to V1 plus V2 plus V3. So how do we calculate the total potential difference? How to calculate total potential difference? If you still remember, from Ohm's law, R equals to V over I. So V equals to IR. So that means if I want to calculate the total potential difference, I use the total current times the total resistance, right or not? So this I can replace with total current times total resistance. Okay, how do I calculate the total the potential difference at V1? I use the current here times the resistance here lah. Same, V equal IR. I want to calculate potential difference here, I use the current here and the resistance here. I want to calculate the potential difference here, I use the current here and the resistance here. I want to calculate the potential difference here, I use the current here and the resistance here. Okay? So that means this potential difference one, we can substitute with I1 times R1 plus this one is I2 R2, this one is I3 R3. You see or not? Anybody do understand how we get this? Anybody do understand? Anybody got any question? Okay, no question. Okay, now we already know that all the current is the same. So that means we can factorize the current out lah. R1 plus R2 plus R3. So this one divided by this one, gone lah. We get 1. Okay, because this current and this current is the same, so we can divide and become 1. So that means the total resistance will be resistance 1 plus resistance 2 plus resistance 3. So you see or not? This is the reason why the way that we calculate the total resistance is this way. Okay, Okay, last time in lower form you just learn, this is the way, right? You never learn what is the reason, but now you learn the reason lah. Okay, any question about the series circuit? Yes.
What if you use a 6-volt drive cell but the resistor only needs 1 volt?
Sorry, one more time.
那个东西只需要15volt，但是我们用6个
The battery， 那个 battery 可以 supply 6 volt， 不过那个灯泡，比如说啦，灯泡只需要1 volt 就可以了，灯泡就会一样，它会得到6 joule 的 energy， 每1 coulomb 经过就会给那个灯泡6 joule。啊？没有，那个每1 coulomb 的 charge 出来，它会拿6 joule 是不是？当它经过那个灯泡的时候，它一样还会丢6 joule 给那个灯泡。那6 joule 那个灯泡会拿6 joule， 所以那个灯泡就会非常好，就是这样子的原因啦。OK 吗？所以如果相反来说啊，terbalik如果那个灯泡是需要6 volt， 不过你放1 volt 的电池罢了，也就是说那个每1 coulomb 的 charge 经过那个灯泡，那灯泡只得到1 joule 的 energy 罢了，所以那灯泡会亮，不过很暗啊，明白吗 ？OK， logic 吗 ？logic OK。The charge when the charge come out from the battery, from the dry cell, no matter how much energy it carry, it will definitely use all of that energy to overcome the resistance inside the circuit. Understand? You understand what he asked us now? What he asked us now is, if we use a 6-volt battery, but the bulb that we put in is only 1 volt bulb, that means the bulb only needs 1 volt, but we connect it to 6-volt battery. What happens is, every 1 coulomb of charge that come out of the battery will carry 6 joule, right? So that means the 1 coulomb of charge that carries 6 joule, when passed through the bulb, the charge will still give all of the 6 joule to the bulb. That means the bulb that only need 1 volt will get 6 volt. So that means the bulb only need 1 joule, but every time 1 coulomb pass through, the bulb gets 6 joule of energy. So what do you think will happen to the bulb? maybe either it will become very bright or it will burn. Understand? This is the reason why if you connect an electrical appliance that need a lower voltage to high voltage, the electrical appliance will damage. Right? Get the idea? Okay, overheat. Okay, actually the reason is because the bulb will overheat. Because a lot of energy go into the bulb becomes very hot, and then it will overheat, and then the filament will melt and break. Okay? Okay, good question. Alright, any other question? Any other question? Okay, next we want to look at parallel circuit. We want to look at parallel circuit. Okay, so you see here. For parallel circuit, last time we learned that okay, let's look at the current first. Okay, let's look at the current first. Okay. Wait. Okay, let's look at the potential difference. Okay, the potential difference. Okay, so for parallel circuit, the potential difference, this one is the total potential difference, the main one, the total potential difference. And the potential difference for each of the component that is connected in parallel is same. They are all the same. The main potential difference will be equal to all of the potential difference. Same. Now the question is, why? Why like that? Because you imagine, it's very simple. You imagine. Again, let's say this is 6-volt battery. That means every 1 coulomb carry 6 joule. So this 1 coulomb of charge that come out here carry 6 joule. So let's say that the current is, let's say that the current is 6 ampere. Let's say. So that means that every 1 second, how many coulomb come out? 6 coulomb. Remember, 6 ampere means every 1 second got 6 coulomb of charge pass through. Okay, what 6 ampere means every 1 second 6 coulomb of charge pass through. So that means every 1 second got 6 coulomb of charge come out. 1, 2, 3, 4, 5, 6. Okay, 6 come out. 6 come out. Every 1 second, 6 coulomb of charge come out. So this every 1 coulomb of charge carries 6 joule of energy. Okay, let's say that this 6 coulomb of charge reach here. Move until here. Now the charge need to decide. Want to go here, or go here, right? Got 3 paths. Okay, now don't care. Don't care if we don't want to think about which path it take first. Every 1 coulomb have how many joule? 6 joule. Let's say, okay, this one, 1 coulomb come here. Pass through here. Here got resistance, right? So the 1 coulomb that carry 6 joule will do how much work? 6 joule of work here. Why? Because after this, got any other resistance or not? No more. So that means only here got resistance. So the 1 coulomb that pass through here will do 6 joule. Okay? If 1 coulomb pass through this one, do 6 joule of work, that means the reading will show 6 volt. The potential difference here will be 6 volt. Okay, now let's say that another 1 coulomb pass through here. Again, the 1 coulomb will have 6 joule. Because from here, from the beginning until here, got do any work or not? No. So fresh, have 6 joule of energy. Pass through here, do how much work? 6 joule also, because after this, no more resistance that need to overcome. So, same with this one. 1 coulomb, 6 joule. So, you see all this reading will show 6 volt. You see or not? As simple as that. This is the reason why a component connect in parallel will all have the same potential difference. Get the idea? Okay, So this explains this why all the same. Any question? No question. Okay, so good. Alright. Next, we want to look at the current. Okay, so let's say that the current is 6 ampere, come out. 1 second, 6 coulomb come out, right? Okay, so this 6 coulomb reach here. Now they need to decide how many pass through here, how many pass through here, how many pass through here. How do you think they are going to decide? Depend on the resistance. Let's say that all these three is the same resistance. If all of them, R1, R2, R3, all have the same resistance, then every 1 second, the number of charge that can pass through is the same. 1 second, here 1 second is 6. So if 1 second, the number of charge that pass through here, here must be the same. That means how many charge pass through here, here? 2, 2, 2 lah, right or not? Remember, just think, imagine, if 1 second, 6 coulomb go to, if 1 second 6 coulomb reach here, that means here, from here to here, total must also be 1 second 6 pass through. 1 second also must be 6 pass through here. Right now, if 1 second 6 pass through here, and all must be the same, so 2, 2, 2 right? Okay? That is if all the resistance is the same. That is what you learn in lower form all the resistance same. But now, what if the resistance is different? Then the charge will distribute according with the resistance. Okay, let's say that this one R1 have have the highest resistance. This one R2 low a bit. This one R3 is the lowest resistance. Highest, low a bit, lowest. So how do you think the charge is going to distribute? This one is more or less? More. Okay? Because if this one the resistance is highest. So the charge that flow through will be less. Resistance high, that means easy to pass through or not? Difficult to pass through. So that means every 1 second, the number of charge that can pass through, of course, will be less because more difficult to pass through. Okay, let's say this R1 is the highest. This one is the lowest. Then that means this current must be the lowest. This current must be the highest. This one in the middle. Understand or not? Low resistance, current easy to pass through. So that means every 1 second, of course, you will have more charge that can pass through. More charge pass through every 1 second, higher current. High resistance, logically, every 1 second, less amount of charge that can pass through. So, lower current. Okay. Okay or not? Any question? Anybody have any question? Yes. 全部跑去最少的那个 它不会的，因为它是会根据那个看哪里一个高哪一个矮，它就会平均跟。最简单的，所以最简单的会有更加多的 charge 走哦，比较难的就比较少啊，还是有 charge 走的，不过比较少，明白吗？就好像说 ，OK， 例如说啦，你有OK， 你有那个拜3条拜 ，OK， 一个大一个中一个小的，你让水流，那个水三个都一样会有水出来的，那个大条的就比较多水哦，小条就比较少水啊，一样的 ，OK ，say OK get the idea， OK 啊 ，so high resistance still got charge going to pass through, but less charge lah. Okay, maybe you would like the question just now. If why not all the charge pass through the easiest one, the lowest resistance? Why not all the 6 coulomb pass through the lowest resistance one? Why? Because in between all the, because across all the resistance got different in charge. Remember, why is it that the charge can flow? Because one side repel, one side attract. Understand? Okay, one side repel, one side attract. So, in between all of this, in between the R1 out, across the R1 out through R3, all of them also have different in charge. That means the charge here is stronger positive, here is stronger negative, positive, negative. So that means still got different in potential. That means still got energy that is pushing the charge to go through here, understand? Here also the same, here positive, here negative. So still got different in charge. So got energy that can make the charge pass through lah. Here also got energy lah. And the energy is all the same. 1 coulomb 6 joule, 1 coulomb 6 joule, 1 coulomb 6 joule, all the same. Okay? So that means the one with higher resistance, the charge will flow slower lah. The one with lower resistance, the charge can move faster lah. Right, same energy. The more difficult one is slower. The easiest one will be faster. Right? Right or not? Is it logical? Anybody don't find this not logical, please make sure to ask. Anybody not clear, please ask. OK 啊，有问题吗？因为我一边在讲，你一边在笑，我就觉得有点担心啊。OK， 是我有今天的衣服有问题呢，还是什么东西？精神有问题，忘记吃药啊。OK， 下次记得吃啊。OK， so that means if like this, okay, wait okay, look at here one more time If 1 second 6 coulomb, that means here also must be 1 second 6 coulomb. Here also must be 1 second 6 coulomb. Okay, so that means total charge here, every 1 second the number of charge that pass through here, the total must be the same as this one lah. Get the idea? Okay, the total charge that pass through I1, I2, I3, the total charge must be the same as this one lah. 1 second 6 coulomb. So here total 1 second must be 6 coulomb. From here to here total 1 second also must be 6 coulomb. Okay? So the total current will be current 1 plus current 2 plus current 3. Okay. Any question? Okay, if no question, we want to look at how to calculate the resistance. Okay, now Same from this current. From this current, so how to calculate the total current? We use V over R lah to calculate total current, right? Total potential difference divided by total resistance, you get total current. So total potential difference over total resistance, you get total current. To calculate current 1, you use potential difference 1 over resistance 1. To calculate current 2, potential difference 2 over resistance 2 plus. To calculate current 3, you use potential difference 2 over resistance 3. Potential difference 3 over resistance 3. So, same like just now. This one, the potential difference all the same. So, can factorize out. Okay? So, this one and this one same. Divide become 1. So, 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. So, this is how you calculate the total resistance for parallel circuit. Anybody have any question? You understand or not? Question? No question. Got question, please ask, don't be shy. Okay. Next. Okay, let's look at example. Number 1, 3 resistors are arranged in series and in parallel as shown in figure. The resistance for R1, R2, R3 are 2 ohm, 4 ohm, 12 ohm respectively. 2 ohm, 4 ohm, 12 ohm. When the switch is closed, close means turn on. Okay, close means turn on. Okay, this one is open. Close, then is connected, then is on. Calculate the effective resistance. Okay, what does effective resistance means? Effective resistance means the total resistance. Okay, effective resistance means the total resistance. So how to calculate the total resistance? You see, this is a combination of series and parallel. So what we do is we total up the parallel one first. R2, R3, we total up first. So 1 over R equals to 1 over 4 plus 1 over 12. So you will get how many? How much? Come on. How much you get? Thank you. 3 ohm. Okay, you get 3 ohm. Remember, this one got 1 over R. So that means this one, 1, you must carry over. So 1 divided by this whole thing. Understand or not? This is the common mistake that students make. After they add these two, they forgot to take this one. 1 divided by this whole thing. Okay? On another word, he forgot to flip over lah. And I also must remind you that the final answer must be in decimal. Never, ever leave your answer in fraction in physics. No fraction, final answer, absolutely no fraction. Okay? In final answer, no fraction. Okay? I say many times. I hope that you remember. Absolutely no fraction, okay, in final answer. On the way to get the final answer, you can have fraction, no problem, but final answer, no fraction, okay. B, the current flowing through the 2 ohm resistor and the potential difference across it. So we want to find the current and the potential difference of the 2 ohm resistor. Okay, so you see this one, this R1 is connected directly to the power source. Huh? What? Oh yeah, thank you, I forgot. Okay, so the total will be the 3 ohm plus the 2 ohm. So it will be 5 ohm. Okay, this is the total one. Sorry, I forgot. Okay, Okay, B. The current flowing through the 2 ohm resistor and potential difference. Okay, so using V equal IR. Okay, if we want to calculate the current, that pass through here, we need to use the resistance here and the potential difference here, right or not? But we only know the resistance, but we don't know the potential difference. So how to calculate this current that pass through here? Okay, so the good thing here is this current that pass through here is the same as the total current, because this current, you see, straight away come from the power source. Straight away come from power source. It didn't go to other place. Straight away come from power source. So that means the current here is the same as the total current. So you can use the total resistance and the total voltage to calculate the total current here lah. Understand or not? So this one we put total voltage, total resistance, calculate total current. Okay, so the total voltage is 6 volt. Total resistance is 5 ohm. So the current will be thank you, 1.2 ampere. Okay, 1.2 ampere. And then, now that we have the current, we can calculate the potential difference across here lah. Okay, the potential difference here. So, same concept. Potential difference here. You want to calculate potential difference here. You use the current here and the resistance here. So, we already have the resistance. We also have the current that pass through here. So, we can calculate the potential difference. So V equals to IR. The current is 1.2. The resistance is 2. So we get 2.4 volt. Okay. Okay, so here is 2.4 volt. And then C. The current flowing through the 4 ohm and 12 ohm resistor and the potential difference across them respectively. Okay, so first the current that flow through them. Okay, so you see, if you want to know the current here, you use the voltage here and the potential and the voltage here or the potential difference here lah. You use the potential difference here and the resistance here. But we don't know the potential difference, right or not? We don't know the potential difference. We only know the resistance. So let's see that we can find the potential difference here or not. Can or not? Can we find the potential difference here? Can. Because you see here and here is parallel. So that means the potential difference here and here is the same. This potential difference here and the potential difference here are the same. Here is 2.4. So that means the charge after pass through here, either pass through here or pass through here. and then go back here, right or not? So that means the 1 coulomb of charge only do work here. After do work here, it will do work here or here. Okay? So that means how much work is done here? How much work? 2.4 joule, right or not? So that means the 1 coulomb of charge have how much energy left? 6 volt minus the 2.4 volt lah, or 6 joule minus the 2.4 joule, so you get 3.6 joule, right or not? So that means the charge that pass through here will do the work of 3.6 joule. Pass through here also 3.6 joule. So that means this potential difference is 3.6 volt. So you see, you get the potential difference here already. So now that you get the potential difference, okay, or we show that we calculate the potential difference lah. Okay, so the potential difference will be 6 minus 2.4, so you get 3.6 volt. Okay, and then after that we calculate the current. Okay, so V equal IR. I want to calculate the potential difference for the R2. I use the current at R2. I use the resistance at R2. So so the potential difference is 3.6. The resist. Okay, I put I2 lah. So this resistance is 4. So the current 2 will be equal to 0.9 ampere. And then V equal IR again. Okay, so the potential difference here at current 3, here R3 is also 3.6 volt. This is current 3. This R is 12. So the current 3 is 0.3, thank you. 0.3 ampere. Okay or not? And you see the total current 2, current 3, 0.9 plus 0.3 is 1.2 ampere. And 1.2 ampere is the same as this one, 1.2 ampere, you see or not? You see, the current that flow through here is 1.2 ampere. Go until here, split into 2. 0.9 ampere, 0.3 ampere, you see or not? Okay, so here to here, every 1 second, 1.2 coulomb of charge. Here, every 1 second, 0.9 coulomb. Here, every 1 second, 0.3 coulomb. So total is still the same. Every 1 second, 0.2 coulomb. And here back to here, of course, is the same lah. Every 1 second, 1.2 coulomb. Okay, so 1.2 ampere also here. Okay, any question? Any question? Okay, if no question, okay lah. In order to save time, I'm not going to discuss this number 2 lah, because almost the same lah. Okay, almost the same. Okay, so we will go to factors that affect the resistance of a wire. Okay, factors that affect resistance of wire. What are the factors? Okay, what I straight away discuss. Okay, what are the factors? Got 3 factors. Length, cross-sectional area, and the resistivity. Got 3 things that affect the resistance of the conductor. First, resistance is, what do you think? What is the relationship with length? What do you think? The longer the length, the higher the resistance. Very logical. Okay, directly proportional. Resistance and the length of the wire is directly proportional. Very logical, right or not? If let's say if 10 centimeter of wire is 1 ohm, if you have 20 centimeter, it's the same like you take 1 ohm connect in series. So you get 2 ohm lah. Right or not? Okay, I show let's say this one is 10 centimeter is 1 ohm. So if you have 10 centimeter, 20 centimeter, so it's the same like 1 ohm. 1 ohm connect in series, right or not? And resistance, if connect in series, the total will be 1 plus 1, so 2 ohm lah. So the longer the wire, the greater the resistance. Very easy concept, very simple, right or not? Okay, Next is the cross-sectional area. Cross-sectional area, that means the thickness of the wire lah. So this is the cross-sectional area. Cross-sectional area of the wire. Cross-sectional area of the wire. Alright, so what do you think is the relationship between resistance and cross-sectional area? Inversely proportional. Very simple. Why? That means, okay, inversely proportional, that means the bigger the cross-sectional area, the smaller the resistance. It's very simple. You see, we use the same concept as series parallel circuit. Just now, if longer length, then the resistance will be higher. So if the cross-sectional area is bigger, it's the same like you are taking many wire connect in parallel, right or not? If the cross-sectional area is bigger. You understand what I'm saying? Bigger cross-sectional area is the same like you are having many wire connect in parallel. So, from what we learned, you see just now, this is 4 ohm, this is 12 ohm in parallel. So what is the total resistance? 4 ohm and 12 ohm. You see 3 ohm only. That means when you have 2 wire connect in parallel, the combined cross-sectional area become bigger. So the resistance becomes smaller. You see or not? Okay, get the idea? So, if the cross-sectional area is high, then the resistance will be low lah. Okay, this is the explanation by using the concept of the series parallel circuit lah. Another simple way of understanding this or remembering this is, we take it that the wire is like a pipe. If the pipe is bigger, easier for the water to flow, right or not? So, lower resistance lah. Bigger pipe, lower resistance. Very simple. Next is the resistivity. Okay, what is this resistivity? This resistivity, the symbol of resistivity is rho. L, this one length is L, and then this one is A lah. So the relationship between resistivity and the resistance is directly proportional. Okay, but what is resistivity actually? Resistivity refers to the property of material to resist flow of charge, okay, or to oppose the flow of charge. So that means resistivity depends on the material. For example, different type of conductor, the resistivity will be different. Iron have its own resistivity. Aluminium have its own resistivity. Copper have its own resistivity. Gold have its own resistivity. Rubber have its own resistivity. And so on. Okay? If you are interested, you can go online and check the human meat, the resistivity of human flesh. It's a very interesting information to know. Maybe it will prove useful in your occupation in the future. Okay? You want to pass through electricity through human meat. Okay? Okay? Right. For medical purposes. Not for torturing or anything else. Okay? For medical purposes. Okay? Really, they do research to find out the resistivity of human flesh, skin, fat, and so on, so that they can research what kind of medical equipment that better to save your life. Understand? How high is the voltage or the charge that need to be charged through your body in order to jumpstart your heart, your brain, and so on. Okay? Like what I say, for medical purposes. Okay? Okay? Not for torturing or anything else. Depend on your creativity. Okay? Okay, now, so resistivity is different for different material. Okay, different material. So, this number of resistivity is determined from experiment. Okay, they do experiment and then they determine the number. So, this number of resistivity is like a constant number like that. So, every material have its own number. Okay, like what I say. Copper have its own number, aluminium has its own number, all of them have its own. Okay, you can go online and look for it. Okay, there's a list. However, there is one thing there's another variable that can affect resistivity, which is the temperature. Temperature also can affect the resistivity. Okay? Remember, temperature affect resistivity, not affect resistance. Temperature affect resistivity, so indirectly it will affect the temperature. That is why a wire that have a higher temperature will have higher resistance, because the resistivity of the material increase. Understand? In higher temperature. Remember just now, previously when we learned about ohmic conductor and non-ohmic conductor, right? Okay, ohmic conductor and non-ohmic conductor. Remember the graph for non-ohmic conductor is curved, right? And we discussed that, okay, tungsten wire is actually ohmic conductor, but when put inside the bulb, it becomes non-ohmic conductor. The reason is because when inside, very good. When inside the bulb, the temperature increased until very high. So it increased the resistivity. It changes the resistivity of tungsten. So indirectly, it caused the resistance of the tungsten inside the bulb to change. That is why the graph for a tungsten filament bulb is not straight but curved. So tungsten filament bulb is non-ohmic conductor. Understand? Okay, Okay, so we combine all these three relationships. We can get R resistance of a conductor equal to resistivity times the length divided by the cross-sectional area. We get this equation. Okay, resistance of a conductor equals the resistivity of the material times the length of the conductor divided by the cross-sectional area of the conductor. Okay, Alright. For those that need to go for duty, you can go for duty. For the rest of you, we continue a little bit more on resistivity. Okay, so I think in the another 2 more page, you can see this table. Okay, so anybody have any question? If no question, then today we stop here. We will see each other again next week. Okay, thank you very much.啊，什么？
它比如讲这个是6V 是6 volt 啊，6 volt 就是6 joule quantum 那你讲它经过每一个的时候都会有6 joule 的 energy 给它。没有。你给了在这个 series circle 里面，如果每个有6 joule， 这不是第一个灯泡就爆掉了？
没有，因为这个每一个它这边还会给多少 joule，它是看它的 resistance 的。如果它的 resistance 高，它就会得到比较多的 energy， 比较多 joule。例如说，OK， 然后我说啊，刚才
没有啊，你刚刚跟阿威解释的
那个例子是 for parallel。
对 ，series circle 是另外一种。
series 不一样 ，OK， 你看我讲解给你看，你看啊，比如说这个1 volt、3 volt、2 volt， 就是说这个1 joule、3 joule、2 joule 是不是？为什么还会这样子分呢？因为它的 resistance 不一样哦。哪里一个 resistance 比较高？
中间
对，非常好，因为它用比较多 energy 嘛，它需要比较多 energy。So 3 joule 比较多，不过总共加起来是6 joule。也就是说，每一 coulomb 的 charge 它一定要经过3个嘛，每一 coulomb 它就有6 joule 罢了。所以它总共在这边，它一定要用，它用它的6 joule全部用到完，在这边3个，明白吗？它不可以好像它6 joule全部用在这个第一个，它用完这个它讲过另外2个，明白吗？有回答到你的问题吗？不过如果是这个的话就不一样。
这个例子建立在这个是1 ampere 的情况下，对不对？
其他 current 也是可以啊。其他 current 也是可以啊。如果我要 current 容易看的例子啊，要其他的例子也是可以啊，其他的号码你要怎么 current 也可以啊。不过就很难，那个号码可能会有小数点啊，所以这样子比较难看。
那我问的，讲 constant 的 resistivity 会 change 掉它的 temperature。
对，当它的 temperature 很高的时候
560是在什么 temperature？
非常好的问题，这个我们全部都当做是在 room temperature， 然后它的 room temperature 是它标定的 room temperature 是20度 ，OK， 在这边呢，在我们 determine resistivity 的这个号码
比较好奇的是它是怎样确保那个 constant 的 wire 可以在好的之外，因为有电流通过的时候不是会变热。
因为在对有电通过的时候它会变热，也就是说它很快咯，它一给那个电一流，它的 reading 一记录就马上帮你关掉，它不要给它的温度上。OK， 其实OK， 我问你啦，如果你只是开你 on 1秒你 on 1秒，你马上你就可以拿到 reading， 马上就可以关掉了嘛，是不是？OK， 在那1秒里面它的温度的确是会上升，不过它不会上很高，也就是说它的 resistivity 它不会改变很大，不会有很大的改变，其实它改变很少罢了。所以这就是原因为什么其他的东西OK， 其实这些全部这些 conductor 我们在 room temperature 里面我们做 experiment 的话，我们都会得到 directly proportional 的 graph， 我们都会得到这样子的，我们都会看到它是 obey 那个 Ohm's law 的，为什么呢？因为它的在 room temperature 里面我们做那个 experiment， 虽然它的温度会上升，不过它的温度的上升是不会上到导致它的 resistivity 有很大的改变，明白？
就是一看就可以看得出它的密在哪里，这个意思是吗？
可以这样子讲啦 ，OK？ 啊，不过如果是在灯泡里面哦，你一按它的温度就上到很高，啊，明白吗？所以它的温度有很大的改变，所以我们就会看到它的 resistance 有很大的改变哦，所以就变成一个 curve 哦。不过其实啦，如果啦，我们在 room temperature 做这个 experiment 啦，如果这个 current 哦，我放给它很大的话哦，也是一样，我会看到它慢慢 curve 的，慢慢 curve。这个我们看不到 curve，因为我们只是一个小段
正常的比较 constant 的 resistivity 的前提，就是它的 minimum requirement 就是很快的速度，很快的时间跟比较低的比较 constant 的，可能是
可以这样讲啊，可以这样讲啊，OK 啊。
这我不明白，这里是全部6Joule，就是讲它让来到这里它会 split，
对，
不全部就会就
OK， 例如说啊 ，OK， 像我刚才讲的 ，OK， 例如说啦，例子我们讲了6 ampere 啦，6 ampere 就是说每一秒有6 coulomb， 是不是 ？OK， 6 coulomb 走到这边的时候，它会let's say 啊，一个 coulomb 走这边，一个 coulomb 走这边，一个 coulomb 走这边啊，我们不管是多少 coulomb 走这边啊，不过每一个 coulomb 走这边的，每一个 coulomb 它有多少 energy？ 6 Joule 是不是？也就是说它经过，它就会在这边，它放6 Joule，它会做6 Joule的 work 在这边。每一 coulomb 经过，它就一定是做6 Joule，每一 coulomb 经过它就做6 Joule，因为没有接下来它就没有需要到 energy 了嘛，就在这一边。啊，就是说这个一个 coulomb 它走这边，它就走这边，它没有可能走这边，它又叫调回来再走这边，它不会这样的。那个一个 coulomb 的 charge 走这边，它就走这边。如果它走这条，它就走这条；它走这条，就走这条。所以也就是说，它只有一个机会用那个6 Joule，就在这边，OK， 一次机会罢了。所以它就会把所有的6 Joule就用在这边了，明白吗？OK 啊。